In geometry, we often have to deal with lines and angles. I mean, geometric shapes are kind of made of lines and angles. And for now, when we deal with these lines, we mean like straight lines, not curves or arcs for now. So, angle relationships. If you have two straight lines that cross, the opposite angles, each pair of opposite angles, i.e. 2 and 4, or 1 and 3, see, they're opposite of each other, they are equal. They are also known as vertical angles. Yes, this is a technically correct term, vertical angles, even though, in my experience, you very much see opposite angles more often. Just vertical angles is a thing. You need to know it exists. Okay? Complementary angles add up to 90 degrees. Supplementary angles add up to 180 degrees. Yes, I realize that this might be a and a bit of brute force memorization, but complementary adds up to 90 degrees, supplementary adds up to 180. There's not that much to be done about it. Like, there's no memory tricks really about this part. Now, if you have a point, you can have lines that freely pivot through that point. An infinite number of lines can pass through a point. But if you have 2 points that are not the same, i.e. they're not exactly on top of each other, they don't overlap. If you have 2 separate points, 2 distinct points, you can only have 1 line that passes through them. So a line is specified by 2 points. A plane, however, okay, let's say we have this as a flat surface, this calculator. Let's say it's flat. Okay, so let's say I have a point here and a point here. Wait a second. Does 2 points specify a plane? Does a plane get specified with 2 points alone? No, you can pivot it. You can pivot the plane along the line between the 2 points. Therefore, to specify a plane, you need 3 non-collinear. i.e. they're not on the same line. So the line is 2 distinct points. Well, it's specified by 2 distinct points. A plane, i.e. a flat surface, is specified by 3 non-collinear points. So 3 points that don't just all line up. If they all line up, well, you can rotate about that line however you like, which means that it doesn't specify a plane. For now, we deal with lines and points. We don't deal much in planes other than a planar shape, i.e. a flat shape. Example, find the value of x. Well, these are opposite angles, so x is 149 degrees. These are straight lines, so the angle they form on that side is equal to the angle they form on this side. How else could you prove this? Well, because this angle adds up to 180 degrees when you add 149, so it's a straight line. They are supplementary, and it's also supplementary on this side. Therefore, this 149 must equal x, because they add the same thing to become 180. Find the value of x in each figure here. Well, x is supplementary with 155 degrees. So 155 plus x is equal to 180. X is equal to 180 minus 155 gives us 25. So x degrees is 25 degrees. 63 degrees and x degrees, well, that's 63 plus x equals 90. X is equal to 27. degrees. Now x plus 77 is 180, so x is equal to 103. And the degree symbol is here, so x is just a number. 128 degrees is the opposite angle to x degrees, therefore x is equal to 128. Remember, the degree marker is already there, so it's just a number. We don't put degrees here because it's already there. For questions 5 and 6, use the figure below. Name the line in 4 different ways. Well, we can say that it's line L as labeled. Line L, AB, AC, or line BC. Okay. If you're looking for the magnitude of BC, like say you put absolute value symbols, that means you want the length of line segment BC. But if you're just talking about line B through B and C, well, this is okay. Name the plane in 4 different ways. Well, it's specified by the point D and 2 other points that are not collinear. You can't have it be A, B, and C because those are collinear. They're on the same line. So it has to be plane DAB, DAC, DBC, and what else? You can also specify a plane with a line that has a direction and 2 points, which don't both lie on this line. In other words, you got 2 points, and then you got a line that points off in a separate direction, which tells you that, oh, we can have a 3rd point somewhere on that line to specify this plane with. So, it can be D, A, L. It seems the obligatory problem-solving section showed up early this chapter. Look, you might have to use, explicitly use, logical reasoning to solve some problems where the solution is not immediately obvious. In general, if you are solving your problems without using logical reasoning, you are probably doing something very, very, very wrong. Okay? You will always use logical reasoning to solve your problems. But as you get more experienced, you don't necessarily have to explicitly use it. Be like, let me think this question over. Yeah, that's what most people think of when they talk about using logical reasoning. And that's why it's, when the solution is not immediately obvious, you may need to use logical reasoning to figure out how you can actually do the problem, which is basically this phase. Select a strategy. So figure out what you're going to do. Yeah, you can use deductive reasoning, which uses top-down analysis. You apply general rules to make conclusions, such as tetrapods are 4-legged animals. A human is a tetrapod, therefore a human has 4 legs. Well, 4 limbs. So that is deductive reasoning. You applied the general rule to make a conclusion. Inductive reasoning is bottom up, and you usually use observations and experiences to form general rules. Let's say we have a flat figure. It has 4 sides. It has only 2 congruent sides and 2 pairs of congruent angles. Is the figure a square, rectangle, parallelogram, rhombus, or trapezoid? Did you use deductive or inductive reasoning? Well, if you had 2 congruent sides and they look like this, and you had 2 pairs of congruent angles, like these, you would be looking at a parallelogram. Yeah, you only have 2 congruent sides, so no. This would have 4 congruent sides. Now obviously we're using inductive reasoning here because we aren't going from rule to conclusion. Because you would have 2 pairs, like top and bottom and left and right, for congruent sides. If it's a parallelogram of any sort, including squares and rectangles or rhombuses, the only choice left in the list is a trapezoid. So it's a trapezoid, right? Well, we have to test. Test. Can this work? The conclusion is, yeah, it certainly can. So, this will work. It has 2 congruent sides and it has 2 pairs of congruent angles. This works. Now, let's say we have some exercises. Use logical reasoning for each problem. Jennifer draws a square on a piece of paper and uses a ruler to draw 1 line through the square to create 2 shapes. What is the maximum number of sides that either of these shapes can have? Well, what happens if you just cut through? This would give you 4 sides on the top shape and 4 sides on the bottom shape. So you'd get 2 trapezoids. But if you cut it at, instead of opposing sides, at neighboring sides, you would have 5 on this side and 3 on the other. So, max sides on either shape is 5. The line has to be drawn through neighboring sides. Above. Line through neighboring sides. Okay, then let's say we have 20 toothpicks. You can make 2 adjacent squares using 7 toothpicks if the adjacent square shares a toothpick for the side between them. So the pattern is 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. So toothpicks. And squares. You get a table that goes like this. 0 squares, 1 toothpick. 1 square, 4 toothpicks. 2 squares, 7 toothpicks. And so on. How many total squares in a row could be created this way with 20 toothpicks? This is going to end up being, well, actually that depends on your format. dot 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 could be like this instead. This is going to end up at, you're adding 3 each time, so eventually you reach 1 plus 18, i.e. 19. And you have 6 squares. Each square gives you an extra 3 toothpicks used over your first initial toothpick. So you would say you can make 6 squares in a row. Alright then. Let's say you and your grandfather have a combined age of 84 years. So let's say you are n years old. Okay. And your grandfather is 5 times as old as you are. That means n plus 5n equals 84. And so 6n is equal to 84. N is equal to, we divide and we get 14. You are 14 by use of algebra, and your grandfather is 70. Geometry is full of deductive reasoning, where you start with a general rule and you draw conclusions from it which you use to do something interesting. Polygons and angles. An interior angle is an angle that lies inside a polygon and has sides that are adjacent sides of the polygon. In other words, it's the angle between 2 adjacent sides of a polygon, such as this angle here. Or if this polygon was bigger, still, this angle here would be an example of an interior angle. This angle here and this angle here also work. You just need to be the angle between 2 adjacent sides of the polygon. A regular polygon has all the sides equal and all the angles equal. Example 1. Find the sum of the measures of the interior angles of a triacontagon, which is a 30-sided polygon. Okay, what's the sum of the interior angles of a triangle? Oh, that's 180 degrees. Okay, let's say we add another triangle. Well, what happens? Oh, look, we have another 180 degrees. And so on. So, for every additional side, we add 180 degrees. So, for n sides, interior angle sum is equal to 180 n minus 2. Now, example 1. Find the sum of the measures of the interior angles of a triacontagon. So a 30-sided polygon. Well, if it has 30 sides, you can cut it up into a lot of triangles. 4 sides we could cut up into 2 triangles. 5 sides we could cut up into 3. 30 sides we can cut up into 28 triangles. Okay then. What does that mean for the interior angle sum? Interior angle sum. You can fit n minus 2 triangles inside just by drawing diagonals. Just a note, when you add another triangle onto the shape, Using one of the existing sides in its entirety, what have you done? You have added two sides and removed one. In other words, you've added one side to the shape while adding 180 degrees worth of internal angle sum. That is part of why the formula works this way. So 180 times 30 minus 2 gives us 180 times 28. So 180 times 28, 5040. 5040 degrees. A 30-sided polygon. It doesn't say if it's regular or not. But that doesn't matter. You can still cut it up internally, whether it's regular or not, into a bunch of triangles. The Defense Department of the United States has its headquarters in a building called the Pentagon, because it is shaped like a regular pentagon. What is the measure of an interior angle of a regular pentagon? So, take two neighboring sides that aren't like flexed inward or something, and draw a diagonal between them that does not go outside the shape itself. That is how you can make sure that all of your triangle's internal angles are part of the internal angles of the overall shape. Like up here with the 30-sided polygon, you could have had a shape that looked like this. And still, you could have drawn triangles. Why? Because for this side and this side, to find this angle, you don't draw a line across the outside. You draw lines across the inside. And it would still have worked. Now, a regular pentagon, you can actually divide the total of the interior angles by the number of angles to find their measurement. Because it's regular, all the angles are congruent, they're all equal. (180) times n minus 2. So 180 times 5 minus 2, 540 degrees. Angle equals 540 degrees divided by 5. So that's 108 degrees. The measure of an interior angle of a regular pentagon is 108 degrees. Let's do some exercises. Find the sum of the measures of the interior angles of the given polygon. Well, the formula is 180 times n minus 2, where n is the number of sides. So this is 180 times 9 minus 2, which gives us 180 times 7. Well, okay, you could write this out, or you could skip down to 1260 degrees. Okay, 17 gone. Yes, that's a way to write this. When you have a large number that doesn't have a specific prefix, or a number large enough that you can be excused for not using a standard prefix. So the sum is 180 times n minus 2. So 180 times 17 minus 2. So 180 times 15. which is going to give us 180 times 15, 2,700 degrees. Okay, how about a 23-sided shape? Well, sum is still the same old formula, 180 degrees times n minus 2, n being the number of sides, n minus 2 being the number of interior triangles you can draw. So, you end up with 180 times 23 minus 2. Substitution step is usually not abbreviated away. So 180 times 21. What's 180 times 20? Well, it's 180 times 2. Oh, it's 360. Times 20, 3,600. Okay, and 3,600 plus 180, so 3,780 degrees. 41 gone. That sum equals 180 times n minus 2. So 180 times 41 minus 2. So 180 times 39. So we multiply and we find this is 7020. Of course, we could have also gone with times 40 minus 1. So yes, times 40, and then subtract 180. Well, after you put in the distributive property, that is. So, it's important in geometry that you check your units, assuming units are given or assuming you're finding an angle. So label units carefully. For these exercises, find the measure of one interior angle of the given polygon. Round to the nearest hundredth if necessary. Interior angle is equal to the sum, which is 180 times n minus 2, divided by the number of such angles, which is equal to the number of such sides. So this is equal to 180 times 6 minus 2 over 6. So 180 times 4. 180 times 4 over 6. That gives us 120 degrees. Now, for a 20-gon, you got interior angle. I'm going to abbreviate it as IA for now. This is equal to the sum, which is 180 times n minus 2, or the number of angles, which is n. So, 180 times 20 minus 2 over 20. So it's 9 times 18. 9 times 18 is 9 times 9 times 2. So 81 times 2, 162 degrees. Now a 36-gon, you got interior angle. Yeah, let's just write this out. Okay, interior angle is equal to the sum, which is 180 times n minus 2, divided by n. So the number of angles to find the average interior angle, which in the case of a regular polygon, because if it was not a regular polygon, we'd be like, well, we don't know. We just know that it has to be less than 180 degrees and greater than 0 degrees. Right? Actually, no, it can be just less than 360 degrees, because you can totally have a polygon that looks like this or something. And you have an interior angle here that's pretty big. So yeah, if it tells you to find the measure of one interior angle of a given polygon, that basically means it has to be a regular polygon unless your teacher is doing a troll question. Like just joking with you guys, which, well, that can be helped. So it's 180 times 36 minus 2 divided by 36. Now that's gonna be 5. And we cancel out the 36 to become 1. So 5 times 34. So 170 degrees. Pentagon, so a 50-sided shape, well, that's interior angle is equal to 180 times 50 minus 2. In this case, I'm just going to substitute right away, divided by 50. Instead of writing out the formula first, the formulas. So 180 divided by 50, well, you see where that's going. 18 times 48 over 5. So 18 times 48 divided by 5, we get 172.8 degrees. As you can see, as the number of sides approaches infinity, n minus 2 and n get closer and closer. So it becomes, well, at infinity, in theory, it becomes 1. So in theory, at infinite sides, in other words, you have a circle, you have an interior angle of 180 degrees. Congruent polygons. Two polygons are congruent if all pairs of corresponding angles are congruent and all pairs of corresponding sides are congruent. The letters identifying each polygon are written so that corresponding vertices appear in the same order. In the case of triangles, what is a trait of triangles that makes them so strong a shape to use in, say, construction of buildings? Well, you can't change the length of any one side of a triangle without changing an angle somewhere. Which means that you have to have a joint failure before the triangle changes shape. Unlike, say, a square or a rhombus or a parallelogram where you can squash it flat pretty easily. The side lengths don't have to change for the angles to change. Whereas a triangle, you try to change one of the angles, the side lengths will have to change, at least one of them. You try to change one of the sides, well, you're going to have to change the angles too. So determine whether the triangles shown are congruent. Here, we're going to use side, side, side congruency. So because AB equals DE, AB is 6 centimeters, DE is 6 centimeters, and I'm using the corresponding points in the same order. And BC equals EF, so 3 centimeters, we're using them in corresponding order. And AC equals DF equals DF. Therefore, by side, side, side congruency, or just congruence, triangles ABC and DEF are congruent. Now there's a few other modes of proving congruence when you have two triangles. You have angle, side, angle. And some people say that angle, angle, side is a derivative of this. But if you think about it, if you have two angles in a triangle, you have the third one, which means that angle, angle, side is actually the same as angle, side, angle. What this means is that, let's say you have the same side length over here, and you have the same angles. Well, if they correspond between two triangles, where could the third vertex possibly be? Oh, it has to be in the extension of the two angles from the endpoints of that same equal side. Even if you rotate it, that just means the whole triangle rotates. They still extend the same way and meet the same way. You can also have angle, side, angle. And yeah, angle, angle, side is part of this. You can also have side, angle, side. Side, angle, side congruence is a matter of, okay, let's say we have a fixed angle here and we got two sticks sticking out of fixed length. And they're the same between two of these sets of shapes. Well, wait a second. Doesn't that kind of specify the positions of all 3 points relative to each other? Yeah. That's why side, angle, side congruence is a thing. Okay. Let's say we talk about these two congruent triangles. Angle ACB is equal to angle EFD, so in corresponding order, equals 90 degrees. Find EF. So the length of EF here is obviously what we're trying to find. It's not find line EF. Here it is. No. So because ABC triangle ABC is congruent to triangle. Hey, we used ABC as our order. Here, the corresponding points are EDF. So it's not in the same alphabetical order, guys. So, what do we do now? Then we go, therefore, AC is equal to EF because you can go because AC equals 5.2 centimeters. Therefore, EF equals 5.2 centimeters. Or you could have gone, therefore, EF equals AC equals 5.2 centimeters. It's just a quirk of the order we wrote these in that make it so that we, depending on convention, you might actually be allowed to go AC is equal to EF equals 5.2 centimeters. Just like that. But that seems to suggest that 5.2 centimeters was coming from the EF side, which it was not. That's why I had these two extra lines, because of the order that this second step was written in. Now let's say we find angle D. Well, because triangle ABC is congruent to triangle EDF, therefore, well, here we're going to go EDF first, and then equals angle ABC, which we have, and that's equal to 60 degrees. Most teachers would be like, oh yeah, okay, with this, but writing one extra line isn't that big of a deal compared to changing up the order during a conversion from congruence of triangles to corresponding angles, because that change of order can actually throw off a lot of people. So what could you do instead? Well, you could also have gone, so because the triangles are congruent, same thing, and then before you start the therefore part, which is the upward pointing 3 dots, the reason why because is 3 downward pointing dots is, as far as I'm concerned, as far as the way I remember it, it's a matter of look down, like it's a downward arrow. And 3 upward pointing points is just reference above. That's why therefore is these 3 upward pointing points. So, the because you'd have the triangle ABC is congruent to triangle EDF. Sure. Okay. This part is the same. But you would also have angle ABC equals 60 degrees up here. And then you'd have, therefore, angle ABC is equal to angle EDF is equal to 60 degrees. Just in case your teacher is a bit of a stickler for seeing that your equal, your final equal, is the thing you're supposed to find and the angle measurement or the value that you found for it. Angle D is angle EDF. Okay, that's kind of important to note because it said find angle D, not find angle EDF. Angle D is angle EDF, so we state this at some point. Maybe at the beginning, maybe at the end. So angle D is equal to 60 degrees. Alright, so let's do some exercises. Determine whether the polygons shown are congruent. If so, name the corresponding parts and write a congruence statement. Well, name the corresponding parts. In this case, we only have the side measurements. Oh, they match up, 5s, 8s, 11s. Okay, it's going to be side, side, side congruence. So, naming those sides are sufficient for name the corresponding parts. AC is equal to FE, AB is equal to FD, using the corresponding points to name the lines, and BC is equal to DE. Alright then, because these sides are equal, therefore, triangle ABC is congruent to triangle FDE. We're naming the points in corresponding order. Of course, depending on teacher, it could also mean that you're supposed to say angle BAC is equal to angle DFE, angle ACB is equal to angle FED, angle ABC is equal to angle FDE. I mean, those are corresponding parts, they are congruent parts, but I'm pretty sure the write a congruent statement coming after means basically prove why it's congruent. In this case, it's side, side, side congruence. Okay, let's say we have two triangles we know are congruent. Find each measure. Angle I Well, our opening statement would be because these are congruent and angle B is equal to 98 degrees, therefore angle I equals angle B equals 98 degrees because they correspond. But I'm pretty sure you don't actually get into that much geometric notation until rather later. So for now, we're going to look at these. Oh, these are congruent. Okay, so B corresponds to I. Angle B corresponds to angle I, thus they are equal because the shapes are congruent. And angle I is 98 degrees. Now IJ is equal to BC because of the congruence and is equal to 15 meters. Yeah, I'm saving us some watching me write time because that notation, we're going to be dealing with it rather later. And in addition, for now, it's the concepts that matter more. Angle H, that corresponds to angle A, equals angle A, which is equal to 180 degrees minus angle B minus angle C. So equals 180 degrees minus 98 degrees minus 46 degrees. So the minus 98 degrees would leave us with 82 degrees. And then minus 46 degrees, well, we end up with 36 degrees. So that's angle H is equal to, angle H is 36 degrees because it's equal to angle A. Right. Well, in geometry notation, you have your becauses, which are 3 points that, if you connected them, make a downward pointing triangle, and you have your therefore statements, which, if connected, form an upward triangle. As I said earlier, the because basically means, okay, look down further, guys. Like if you connect them, that's a downward triangle. It totally says, look down further. And therefore is, for reference, see above. Okay, these are important. You'll be using them a lot later. In North America, we basically do symmetry as early as we start doing math and any appreciable amount of shapes. A figure has line symmetry if it can be folded over a line so that one half matches the other half. This fold line is called the line of symmetry, and some figures have more than one line of symmetry. Some figures, such as a circle, have infinite lines of symmetry. Determine whether the equilateral triangle below has line symmetry. If it does, draw all lines of symmetry. If not, write none. Well, what happens if you fold it in half like this? Oh, it matches up. And because it's equilateral, it matches up that way as well. And that way. So it has 3 lines of symmetry. A figure has rotational symmetry if you can rotate or turn it less than 360 degrees about its center so that the figure looks exactly as it does originally. The degree measure of the angle through which the figure is rotated is called the angle of rotation. This figure, what happens if you turn it over? Oh, it matches up. Just like all parallelograms do. So, it has rotational symmetry. And it has to be rotated 180 degrees to line up with itself. Exercises. For 1 to 6, complete parts A and B for each figure. A. Determine whether the figure has line symmetry. If it does, draw all lines of symmetry. If not, write none. Determine whether the figure has rotational symmetry. Write yes or no. If yes, name its angles of rotation. Well, this is an isosceles triangle, very visibly. So it has one line of symmetry. And rotationally, we write no. Now, wait a second. Up there, it said, if not, write none, and then write yes or no. And if there are lines of symmetry, you don't have to write yes, you just have to draw them. This means we don't actually have to state rotational, no, versus lines, no. None and no are different in this context. So, this is a square. So we have two lines of symmetry, and then we have two more lines of symmetry. So if this is a square, is a square as it looks. Well, in this case, it's as square as it looks, i.e. is a square. So it has rotational symmetry because you can rotate it 90 degrees and it fits on itself. So our answer is yes, 90 degrees. This shape, it has none, no lines of symmetry, and no rotational symmetry, because you can't rotate it any amount less than 360 degrees and have it cover itself. This heart here, well, it does have a line of symmetry. Rotationally speaking, though, no, it does not have rotational symmetry. This rhombus, it has two lines of symmetry. And as a parallelogram, it has rotational symmetry. Specifically, it has 180 degrees as its angle of rotation. Yes, 180 degrees. This right triangle has no lines of symmetry because it's not isosceles, and its angle of rotation, you end up having to turn it 360 degrees, which means it has no rotational symmetry. So it's none and no. When you reflect a figure across a line, every point on the reflection is the same distance from the line of reflection as the corresponding point on the original figure. That means you're drawing perpendicular lines to the line of reflection, and you're making sure that they are the same distance away. And same here. This is approximate, by the way, this diagram. And same here. So you're drawing perpendicular lines that are the same length. And then you're connecting them. Yeah, please use a ruler if you can. So the orientation of the image is different from the original figure because it's been reflected. And the image is congruent to the original figure. For example, if you draw the image of triangle ABC after reflection over the given line y equals 0, what happens? Oh, hey, here you got 4 units, and you go 4 units across, down. Well, here it would be a cross if it was if we consider this to be a cross, but well, usually people don't. Here it's 5 units perpendicular distance to the line of reflection, and it's 5 units away then. Along the same line, we extend that same line, which is perpendicular to this. And here, B to B prime, oh, it's 1 unit. And we extend it by the same 1 unit on the other side. And it's also perpendicular to the line of reflection. Okay, well, let's draw a few images of reflected figures. So we have this figure. That means we gotta go 2 units. So 2 units on this side. Okay, that's over here. So 2 units on this line extended. And then that's gonna have a 3 unit long line. It's not convenient to draw another, so I just left it like that. And over here, oh, that's 4 units. Which means this has also got to be 4 units. So we go to up here. And that means we're looking at a shape like this triangle here. This figure, it actually has the points labeled. Now we use the prime symbol to mark reflected points or translocated points generally. So it's 1 unit on the other side, 3 units on the other side. So C prime. And here we have 4 units on the other side. And here we have 3 units and 3 units on the other side. Okay then, we connect these points. Please use a ruler to draw your diagrams if you are capable of doing so. Unfortunately, I can't use a ruler on this. So, A prime and B prime are these 2 points. So you should get something like this. It gets a little bit more complicated if, say, the line of reflection is on a slant, but you can use perpendicular lines of equal length to find where the points you're looking for will end up. Translation is something you've probably done in much earlier grades as well. Reflection, you probably also did that, but translation is probably one of the first geometric transformations you deal with on grid paper. So when a figure is translated, every point is moved the same distance and in the same direction. The translated figure is congruent to the original figure and has the same orientation. So let's say we have triangle ABC and we translate it 4 units left and 6 units down. Oh, hey, A is translocated that much. It's translated that much specifically. And C is translated the same amount to C prime. B is translated the same 4 units left and 6 units down to B prime. I'm going to draw these as 6 down and 4 to the left. The order doesn't actually matter. just so that I can actually draw all of them without having any of them intersect. Okay? So those are the illustrations of how the translation worked. Technically, they're all supposed to be drawn the same, but drawing A crossing through C is, or C crossing through A, that's not perhaps the most brilliant idea known to man. Exercises. Draw the image of the figure after the indicated translation. 5 units right and 2 units up. 1, 2, 3, 4, 5 to the right and 2 units up. That means C prime must be over here. And we know that A is 2 grids over and 1 grid down, so A prime is over here. And to check, we can go, 1, 2, 3, 4, 5, and then 2 up. Okay, we did it correctly. B, because it's not really close to the others, it's not a good idea to reference off the transformation we already made and the relative locations of the points to plot the other point. B, we have to translate separately. 5 units right, 1, 2, 3, 4, 5, and 2 up, we'll leave B being over here as B prime. Okay then. Now we would connect these points to make the shape. All right. Of course, you should use a ruler if you can. 2 units right and 5 units down. Well, 2 to the right and 5 down. 1, 2, 3, 4, 5. Put A prime over here. B is going to be 2 units to the right and 1, 2, 3, 4, 5 down. So B prime, oh hey, it's 3 over and 1 up from A prime. Just like B is that much from A. Okay, good. We're not making any problems yet. Or at least if we made a mistake, it was consistent. C, well, you can reference B and find C prime. And D, you can reference C very easily for D prime. To check, you can go, is this 2 units right and 5 units down? Yes. Okay, good. All right then. Now you connect these points and you should use a ruler if you can. Sadly, I have equipment issues for that. Alright, 6 units left and 2 units up. 6 units left. 1, 2, 3, 4, 5, 6. 2 units up. 1, 2. That's over here for A prime. And C, it's from 6 to 0, of course. And then 2 units up. C prime is over here. Yep. 4 over 1 up. Matches up. B, 6 over and 2 up. B prime. So you're dealing with this triangle. Now, if you want to move this thing 7 units left and 1 unit down, you gotta count, right? Actually, you can just math it out, because like 3 minus 7, 7 units left, that's minus 7 on the x-axis. That's negative 4, okay. And then 1 unit down, oh, we're going from 3 to 2. So you can do this by graph paper, or you can take A, 3, 3, and add the transformation of 7 units left and 1 unit down. Negative 7, negative 1 equals A prime at negative 4, 2. So yeah, you can use math for this. But of course, if you have a grid, why not use it? For B, 2, 1 unit down is going to be a 1. Okay, and where is this horizontally? 7 units left from 6, that means negative 1. B prime. This is A prime. And the C prime is going to be 2 above B prime. So let's check if we did that correctly. 1, 2, 3, 4, 5, 6, 7 left and 1 down. Okay, great. Also, the math works out. And then you connect your points to make the shape. You're supposed to use a ruler if you can. Sadly, I can't. Well, then. That is it for this chapter, where we talked a bit about geometry and reviewed some of the transformations that we've been doing for probably a long time in the case of translations. Well, that's it for this chapter. See you next chapter.